All right, we've been talking about energy, and we've talked about three different types of energy. All of them fall under the umbrella of mechanical energy. Mechanical energy is an energy that has to do with mechanics, which is the study of motion and its causes. So it's where something is, how fast it's going, what forces are on it. And so we want to talk about mechanical energy and the conservation of mechanical energy. So when we look at this, mechanical energy is the sum of all the kinetic and potential energies that an object has. So if we look at mechanical energy, it's just kinetic energy plus potential energy. But we have two different types of potential energy that we've talked about now. We've got gravitational potential energy, and we've got elastic potential energy. So our formula, if we want to think of it as a formula, is the sum of kinetic energy plus gravitational potential energy plus elastic potential energy. So when we look at this, then we want to talk about how the energy changes from one type to another. And when we do that, we want to keep in mind a law of conservation. Now, in chemistry, you had conservation of mass, where you had to have balanced chemical equations. Now we have conservation of energy, and the energy is conserved to give us the total amount of energy be at any point in a situation stays the same. The type of energy is different. So what might have started out as gravitational potential energy might be kinetic energy. That's like a fall. If something falls from a great height, it had a lot of potential energy at that point, but it falls down when it's landing at a zero potential energy, but it's all kinetic energy. So it's sped up to the point where all of the energy is changed to kinetic energy from potential. But the same amount of energy is there at all points in time. Halfway down, half of it is potential energy due to gravity, half of it is kinetic energy. So the total remains the same. So if we can find at any point how much energy there is in a system, we can apply that at any other point. Now, it makes it challenging sometimes if there's multiple types of energy present. But what you want to do is keep track of each type of energy. And there's three overwhelming questions that you want to ask at any point in time, at any instant in time. The three questions are these. Is the object moving? If it's moving, it's got kinetic energy. All right. Well, kinetic energy is found if we know its velocity and its mass, 1/2 mv squared. All right. The second question is, does it have any height? If it's got height, if it's not at the lowest point it can go, then it has a measurable amount of height. If it's at as low a point as it can go, then it's got zero height. But if it's any higher than that point, if the answer is yes, then it has potential energy due to gravity. And we can apply mgh. So we have to know the mass and the height. Okay? The third question is there stress or strain in the system? Is there something that is bent or deformed from its normal shape and it's going to spring back into its normal shape? If it is, that means that it has potential energy inside of it due to elasticity. So if the answer here is yes, then we've got elastic potential energy, and we can apply what we just learned, 1/2 kx squared. So those are the three questions to ask at any instant in time. So is it moving? If it's not moving, there's no kinetic energy at that point in time. Does it have height? If it doesn't have height, there's no gravitational potential energy at that point in time. Is there stress or strain somewhere? If there's no stress or strain, there's no elastic potential energy. Now, what happens then is the energy at any instant in time. Now, we'll talk about initial and final, but you can compare any two instants in time. All energy at one point in time is equal to all the energy at any other point in time. So it doesn't have to be the initial point and the final point. It can be any other point in time. So the kinetic energy and potential energies at one point in time is equal to the sum of the kinetic energy and potential energy at another point. And that tells us then that we have this big, long, really intimidating formula, because potential energy, there's two different types. Now, the whole key here is to figure out when certain types are not there. All right. A lot of the time we don't have elastic potential energy. If you're going cliff diving, you're staying at the top of a cliff and there's nothing stretching or straining other than maybe your brain is stressing about jumping. But if you're going cliff diving, you've got gravitational potential energy and nothing else. You're not moving, you're standing at the top of the cliff. If you know how high that cliff is and how much mass you are, you know how much energy you have, mgh. If you jump off that cliff and fall from that point, what happens is your gravitational potential energy, which is calculatable based on the height of the cliff and your mass, starts going down because the height is going down. But you start speeding up. So your kinetic energy is increasing. Halfway down, you've got half the gravitational potential energy that you did, but the rest is all kinetic. If you know your mass, which you did to find your gravitational, you can figure out how fast you're moving. As you continue to fall, when you hit the water, you've got zero gravitational potential energy, and all that energy that you had is kinetic, and you can figure out how fast you're hitting the water at. The basis of this energy conservation is really the basis of our kinematics equations, because the mass didn't change. So if the mass is the same here and here, we could essentially take this formula and cancel out masses. And that gives us a one-dimensional motion equations. Final velocity versus initial velocity, final height versus initial height, which is delta y in our one-dimensional motion problems. So I highly recommend looking at this formula skeptically, because this is not how we generally approach it with all 6 of these equations. We generally find spots where there is no height, so mgh is gone. So if you start out where there is no height and you shoot something up, then mgh is 0, mvi is 0, and all your energy is elastic, like a spring that's shooting something up. So now you have 1/2 kx squared equals, well, maybe you measure how high you get. At that point, the highest point, you're not moving, so there's no kinetic energy. There's no elastic potential energy. It's all gravitational potential energy. So at that point, you can figure out, based on how high it is and the mass, you can figure out how much energy something had. All right? So we look at initial and final, but we don't necessarily, it doesn't necessarily have to be the absolute initial, the absolute final. It can certainly be any point in time, as long as we're looking at all 3 types of energy at the same point in time. And we're asking these 3 questions. Is it moving? Does it have height? Is there stress or strain? And oftentimes we can find spots where only one of those exists. So it simplifies our formula tremendously, because the other 2 would be 0. Okay? So that's really what you want to do when you're given situations like this. We're going to do some lab stuff. We're going to do some different stuff. But what we're doing now is really talking about the concepts. And then when we use the formulas, we have to put the concepts into practice and find the numerical values. If we know masses, velocities, or heights, or if we know the elastic potential energy involved in something. Okay? So what changes when something falls? The gravitational potential energy decreases and the kinetic energy increases. All right. However much energy it loses due to gravitational potential energy is how much energy it gains due to kinetic energy. So we have to use mgh and 1/2 mv squared. If something is stretched or compressed, we can convert both kinetic energy and gravitational potential energy into compressing a spring, for example. So if something is thrown upward, that's a fall. So the energy, the work that I put into this is equal to the energy that it has at the highest point relative to my hand. So whatever happens, I can look at different points and look at that. So if we don't have the mass cancels out, and we can, since the mass of the object stays the same, we can do that. Okay, so when we look at that, here's what I want to do. We have a Socrative going right now, and the address is right down here for the website, or you can use the Socrative app on your iPad. And this is a conceptual exercise in a bungee jump. If you've ever been bungee jumping, you're lucky. I'd love to go sometime. But that's a great example of what's happening in terms of energy. Now, in real life, there is a little bit of energy loss. If there wasn't, the bungee would snap you right back to the bottom of the bridge and smack you into the bridge. But we're going to treat it like the energy is conserved the whole time. So we see these 7 questions. These 7 questions are replicated in the Socrative. So go to Socrative.com and log in with your student ID in the room. Mr. Dooley and I have sent out the room addresses for you guys to use either the Socrative app or Socrative.com to log into those and answer those. After you've done with that, then we have some problems to answer for the video lesson. So answer those questions. And then finally for today, we have a simulation on the PhET app on your iPad that is the skate park simulation. So if you go to the PhET app and open that up, and there's our spring Hooke's Law thing, but we go to skate park challenge. Where'd it go? There we go, energy skate park, right there. And we want you to try this out and figure out how the energies are converting from one type to another and looking at that. Play around with it, answer the questions, and that's what we got going on today. All right. Thanks a lot. Have a great day. We will see you on Thursday or Friday.